TCP, BGP, K8s, CMOS, RAG, UEFI. Modern computer science relies on over 1,000 standard acronyms. This shorthand serves a purpose beyond saving keystrokes. Each term defines a strict interface of abstraction. These layers hide internal complexity, allowing a subsystem to function as a simple building block for the logic above it. Mapping this dictionary reveals a single, cohesive, five-layer architectural stack. Understanding this taxonomy is the primary requirement for a systems architect. Layer 1 is the physical realm of bare metal hardware. The foundation consists of integrated circuits, or ICs, mounted to printed circuit boards, known as PCBs. These boards route electrical signals between components along dense trace pathways. The central processing unit utilizes an internal arithmetic logic unit to execute mathematical operations. Early microprocessors demonstrate the physical origins of this processing architecture. Data retention has moved toward the high speeds of non-volatile memory express, or NVMe, leaving behind the mechanical limitations of legacy hard disk drives and their spinning magnetic platters. When the hardware first initializes, it moves from the legacy BIOS interface to the Unified Extensible Firmware Interface, or UEFI. Ultimately, Layer 1 transforms raw physics into a stable binary environment, shielding the software engineer from the underlying electrical engineering. To move data beyond the local machine, we use Layer 2, Network Transport. A Network Interface Card, or NIC, serves as the bridge, identified by a unique Media Access Control address. This hardware provides the physical exit point for digital information. Transit occurs across the TCP/IP stack, the global standard for navigating the internet. Global traffic is directed between massive networks by the Border Gateway Protocol, while Open Shortest Path First handles the internal routing. The domain name system abstracts numerical IP addresses into the human-readable URLs we use daily. Layer 2 completely removes the constraint of physical distance, making massive remote data centers as instantly accessible as your own local components. Layer 3, infrastructure, detaches software environments from specific physical machines. Hypervisors create virtual machines that subdivide physical resources into multiple independent environments. Microservices architecture further refines this using agile Docker containers. Orchestrating thousands of these units requires a control plane like Kubernetes or K8s. This model is commercialized as Infrastructure as a Service, or IaaS. Code is deployed into this virtual environment through continuous integration and delivery pipelines. Layer 3 entirely abstracts the data center, allowing modern engineers to provision massive scale through code rather than manual hardware installation. Layer 4, data and application logic, is where user intent is processed. Application state is managed by either table-based relational databases or flexible NoSQL architectures. Communication between internal data and external software is handled by application programming interfaces, or APIs. These systems exchange data via REST protocols using JavaScript Object Notation, or JSON. This information is ultimately presented to the user through a graphical user interface. Early personal computers established the precedent for abstracting command lines into these visual environments. Layer 4 converts machine data streams into interactive human workflows. Layer 5, the cognitive layer, is the newest addition to this stack. Machine learning and deep learning architectures sit atop the application layer, identifying patterns within structured data. This compute-heavy work requires specialized hardware accelerators back at Layer 1, specifically GPUs and TPUs. The primary reasoning engines of modern AI are large language models. We ground these models in factual data using retrieval augmented generation, or RAG. Safety and alignment are achieved through reinforcement learning from human feedback. To generate a single output, these massive models must instantly process hundreds of thousands of simultaneous probabilistic weights across vast neural pathways. Layer 5 shifts from the deterministic logic of standard programming toward human-like reasoning. This creates a single, unified framework. Every term in the computer science lexicon exists at a precise engineered altitude, from CMOS at the base to LLMs at the apex. A developer at the application layer can execute complex logic without interacting with network routing or the underlying physics of the hardware. A single prompt slices instantly through every layer, moving from high-level reasoning down to the movement of electrons and back up again. This vertical integration allows modern software to operate at global scale. Silicon hardware provided the initial foundation for this digital expansion. The development of strict abstraction boundaries enabled the construction of systems far beyond the capacity of any single human mind. This dictionary of 1,000 terms provides the architectural stability required to manage the immense complexity of modern computing.